David works as an automotive software architect at a major automotive Tier 1 in Germany and has been forced to stay at home for a few days. He's just received a call from his colleague Nicholas, a function developer who has finished the new functional model of the loop controller. It now needs to be integrated into the ECU. Nicholas wants to know whether it still fits into the available hardware. David wonders how he can quickly verify if the ECU hardware has sufficient resources to meet the needs of the new loop controller. He also wants to avoid lengthy testing on the hill, something he can't access from home anyway. A model-based verification with a simulation could help. He's going to have to verify the end-to-end latencies from the sensor to the actuator and simulate artifacts such as task preemption as well as memory and bus arbitration. And, not to forget, effects such as jitter or drifting clocks also need to be considered for meaningful results. Is that even possible? David recalls that he had already successfully used the Inchron simulator on these aspects of the design at the much earlier architectural phase of the project. By reusing this existing model, only a few further steps will be needed to integrate the new loop controller. Back then, only expert estimates for the runtimes of the tasks were available, but now he has the accurate measurement data captured during previous hill tests, so he can simply import that trace file into the model. He checks back with Nicholas to ask him his opinion on the execution time of the new loop controller compared to the previous version. He guesses it will need about 10% more time. As they talk, he also highlights an observation he made earlier about there being too much jitter in his input signals. In order to avoid that in the future, David defines a new start-to-start jitter requirement using the Inchron tool suite. With this new requirement captured, David starts the simulation. A real-time requirement violation is almost immediately highlighted. With just one mouse click, the Inchron tool suite jumps to the instance in the trace where the problem occurs. He quickly identifies the root cause. A high priority task preempts right before sensor sampling should occur. Only a few clicks are required to increase the priority of the sensor sampling task. Done. This real-time requirement is now fulfilled. Looking into the sporadic end-to-end latency violations, the timing diagram highlights the problem easily. A task mistakenly mapped to this core preempts the time-critical event chain of Nicholas's loop control algorithm. Because it isn't necessary to run through a complex build process, the task can be simply and quickly mapped to core 1 in the simulator. David is now satisfied and Nicholas's requirements have all been met. After a few further optimizations, all of the project's remaining timing requirements are fulfilled. David reports to Nicholas that the new loop controller fits into the existing hardware. Nicholas is impressed that David was able to undertake this in just a few hours. He will recommend that his team establishes this simulation-based approach in future projects. Without David's speedy assistance and Nicholas's precise specifications, the team would never have been able to keep to their tight release schedule. At Inchron, we see excellence in timing for embedded systems as a partnership to attain an absence of sporadic timing errors by design, achieve predictable project schedules through virtual verification, and maintain high quality standards by efficiently mastering real-time system performance. If you'd like to experience it yourself, then get in touch to request a free 30-minute consultation with one of our timing experts.